So Willem and I have been working together now for about 3.5 years at Booking.com. We were the original members of the Booking.com security program. I'd like to thank Ryan for giving a nod to security teams as facilitators. That's what we definitely try to do. And this is one of those projects that came out of that concept of let's build something that's useful for us, but isn't just useful for us and might add value in other places. So a little bit about our backgrounds. I have more of a programming background, and Willem has more of a system administrator background, but we both have been doing security forever. Ever since we started into computing, we ran up against things for myself. I got my home Linux server owned by running bind, so thanks to Peter for Power DNS and such. And we do this stuff at Booking.com. So we do it at quite a large scale, and agility is a huge focus of the company. So we can't get in the way of anyone at Booking.com. Wanted to kind of give you an overview of what you can expect from us. We started into this thinking about what could we tell you about logging, and it turns out this is quite a large topic, so we're going to try to cram it all into 45 minutes. Hopefully we'll get through most of the presentation in that time, but there's quite a bit to go over. We're going to talk a little bit about the lessons that we had learned by building ElasticSearch clusters, by parsing data, throwing things into various storage backends and seeing what we could get out of it. And then we're going to actually show some investigations that we've done in the security team and some of the other uses that we didn't expect people to use these tools for that they were able to get additional value out of. There's a few assumptions that we have. At Booking.com, we have an amazing business intelligence platform already. It's so good that most of the time the business people are the first to notice there's a problem with the site before the engineers do, because engineers are looking at uptime, load averages, CPU, throughput, page requests. The business analysts are looking at the conversion rates, and the business guys are the ones who notice the site goes down first, which kind of scared me when I started working there. All of our production servers run Unix. So it's Linux most of the time, so we have a certain tool set that's available to us. And Willem and I are security engineers, so we came at this from the mindset of a security person. And part of the problem with this was it started as a project that we kept pitching to management, saying we want to make the central logging better, we want to make it better. They're like, tell us the value. We're like, well, if we build it, they will come. It was kind of that type of mentality. We couldn't really express in words what would come from having all of this data in one place, especially when the business intelligence was already so good. We actually did have Splunk come out to take a look at what we were doing, and they could not justify selling us licenses because our business intelligence was already there, and that's what they were kind of selling as the cool thing that they could do. So we do web scale logging. And we use syslog as a transport mechanism for this. The reason why we started, it's all already installed on the servers. We are using SYSLOG-NG on all of our production servers because the configuration is really easy to understand, but don't do that, please. Use rsyslog. It's already the default in most of the distributions out there, and its features are quite significant. When you do this, remember that all syslog calls in your applications will be blocking. So if you're just going to syslog everything, you might run into some performance problems. A classic example is IP tables. If you add a target of the log into an IP tables rule set, you can actually cause dramatic network degradation because of the time it takes for syslog to flush that message to disk. So why rsyslog? rsyslog is great. It supports all of these outputs. It's really awesome for supporting some features that some other transports don't, like ElasticSearch, MongoDB, and Kafka. And of course, you can email your log entries to people. I would love to do that sometimes to the CTO just as a joke. SYSLOG-NG, though, is how many people are using SYSLOG-NG in their infrastructure? Okay. So there's some things that are kind of interesting about SYSLOG-NG. The configuration is very easy to read. This is beautiful, right? You guys have seen traditional syslog configs, and this one is readable. I mean, if it doesn't matter if I'm a developer, a system engineer, someone in IT help desk, I can read that last line and understand what's happening. There's one problem actually, there's more than one problem with that. Does anyone notice anything that might be wrong with this? It's kind of subtle. It's two things that are kind of subtle. So we end up with a silent discard here. We have something that's come into the logging stream that is being discarded without notification. That is anything that's matched our filter. The other thing is that if you're tailing access logs, your access logs tend to get a lot of hits. So there's a lot of I/O that's occurring. And SYSLOG-NG will implement polling using either ePoll or iNotify to forward that log on to additional destinations. This can cause CPU, a large amount of CPU usage. So what engineers have done as a way around this is use follow frequency instead. Has anyone seen this type of thing in a config file where you have a follow frequency 1 in SYSLOG-NG? Basically just says, after every 1 second, wake up, check the file if it has new content, and then flush that information out to the syslog system. Sounds great, cuts down on performance overhead, everything looks great except for one thing. The default limit is 10 lines of log entries back. So essentially, without setting this log fetch limit in SYSLOG-NG, silently you're losing all the rest of your data. So you may be logging potentially hundreds or thousands of requests per second on a server, but SYSLOG-NG is only forwarding 10 per second to your upstream logging system. Syslog isn't web scale. Is something that I've heard a lot. There's a lot of other projects out there. If you're looking specifically for something that is hot or trending, you might want to take a look at some of these other technologies instead for pub/sub-queue style systems. Apache Kafka is really nice. It allows you to integrate natively with data analytics platforms like Spark. So you could actually begin to hand your syslog data over to analysts simply by streaming your messages into Kafka. If you're looking for something a little high performance, then you could go with something like NanoMessage. I've seen people using Redis as ways of transporting log data around. It's not really a queue, but people continue to use it like that. And then RabbitMQ, ActiveMQ, so on. It's also not a logging pipeline, right? So it's not going to hard code the transport things into structures, and you're not going to be able to log native data structures in your applications. If you're looking for that, then Apache Flume or Facebook Scribe might be a better fit. They weren't for us. And it's not a full logging platform, right? Syslog is just going to take your message from a server and send it somewhere else. If you're looking to pull a lot of analytic data out of that and you don't want to do that at the endpoint that you're transporting to, but instead in the flow, then you could take a look at these projects. How many people have heard of Logstash? How many people are using Logstash? It's kind of the de facto standard of shipping these logs into ELK, the ElasticSearch Logstash Kibana ecosystem. And it's great. It's very configurable. But what we found was at the time we implemented what we have, it could not handle over 1,000 messages per second. And we were looking at about 45,000 messages per second we needed handling. FluentD is also an alternative to Logstash. It's a little bit more lightweight and a little bit faster than what Logstash does, but it's very similar. But if I were going to start with something today, I would look at Heka as a way of transporting all of my logs and providing this as a consistent platform. So the thing is, syslog is boring technology, right? It's not going to be like Heka to set up. It's not going to be like Heka to configure. But I would argue that we need a lot more boring technology because it simplifies our endpoints and gives the endpoints more processing power to serve our applications and to serve our customers. And we can hire 1 million sysadmins right now that understand how syslog works. So we've increased our hiring capacity, and we've also simplified our application, given more capacity to the endpoint. This may not be true for your environment. You might find additional benefits from doing something different with it, but that's really up for you to decide. So you can just do whatever you want, but it's much easier just to blindly trust me. Our syslog infrastructure right now is functioning at about 90,000 messages per second consistently, and then bursts to over 125,000 messages per second when some appliances flush their caches. So now that you're throwing logs through syslog, at some point you're going to parse the logs. Something like Logstash has built-in filters they use Grok and a few other filters to chunk messages into tokens. And there's some things that we learned while we were doing this at high scale that aren't incredibly obvious at first. The first step is just to retrieve the basic information out of syslog, out of your logging data. When something happened, which server sent the logs. Always use fully qualified domain names when you're logging information from servers. What level was it? Was it an emergency? Was it crit? Was it just debug info? What generated the logging message, and then what was the content? And you get this for free. All of this is part of the syslog RFC. So you might want to go beyond that, because simply just having the content of the message may not be enough to do anything fun with. So you're going to look to get more information out of your logging system. So like I said, if you use fully qualified domain names, you might also have data center IDs in your fully qualified domain names. You might have environments, so whether it's a production environment, pre-production, test, QA, those might already be a part of your domain system. And that's metadata that you already have available that's already in the system. So you can extract that very quickly without having to query any external data sources. Well-known log formats can easily be tokenized. There's probably 1,000,001 Apache access log parsers in every language, and probably most of you have already written one yourself. Raise your hand if you've written an Apache log format processor. Yeah, so I mean, we can get more information out. Another thing that we decided to do was allow developers to syslog JSON, and then we just have a really simple match that sees if there's a curly brace in the syslog message, and if there is, it substrings from that point on and attempts to parse it as JSON and then pull those keys values directly into a document. So it's a really simple check that adds almost nothing to the latency. There are some shouldn'ts. These are shouldn'ts because I don't like to say don't do these things. They might make sense. Bad regular expressions will completely choke your logging pipeline. And a bad regular expression is any regular expression you haven't benchmarked. How many people benchmark regular expressions? Yeah. How many people write regular expressions? Yeah, okay, so if you're writing regular expressions and you don't understand whether your language is implementing them in DFA or NFA, you could really be messing up your ability to process data and wasting cycles. This regular expression is terrible. And we also found that making calls, even a simple call to DNS, can actually increase the latency of the log processing time so significantly that you would have to scale orders of magnitude in order to handle from simply doing the reverse lookup at the time, doing a DNS lookup at the time the data is retrieved instead of doing it when the data is actually indexed. But again, these things may vary for your use cases. So after we've gone through this, after a message has come through our system, we end up with a document. And this is just represented in YAML because it's very condensed. But you can see that we had a syslog message that came through, and we were able to extract this information from it. And you can see it has all of the log stash style fields in it. Just basic information, no external lookups were necessary. Everything that you see there just came out of that log entry. But we decided, especially security guys, that we could do better. We could parse out the refer information so that we could handle that as a normal URI, split it up into pieces. That way we could pivot in our searches off of those pieces. We could parse the resource parameters in the URLs and look for things that are interesting to us, like book numbers, hotel IDs, usernames, session keys, anything that might be interesting to retrieve later or pivot on, we wanted to be able to see. So we were just able to pull that out of the data. This was, again, not using any external sources, just pulling data out of what we had available. And we also used the GeoIP stuff that MaxMind provides because it's pretty quick. And now we're making lots of money. I'm not going to say that the two are related, but yeah. So after going through this process, we were able to add some additional context to a log very simply. Here you see, and we'll get a little bit more into this, is that we score every single URI that's requested from our front end against a very simple attack scoring system that will tell us whether or not someone is attempting to hack our system. We also get we pull out the chunks of the refer that we think might be interesting to pivot on later. What we also do with this refer parsing is we parse the full URI. So if the username element comes through in a refer, we know that someone might be trying a phishing attack, with booking.com : or booking.com at some bad guy URL. So we parse all of that information out, and then the GeoIP stuff.
So yeah, not just a pretty face. Basically, all of the fields that Brad is talking about is real live incidents that we had that we decided to add because we needed those pivot points to do searches back to guess impact, to see the extent of attack. So a lot of people would look at the attack scoring thing like XSS, we detect XSSs and SQL injections. So why not use a web application firewall? How many of you use web application firewalls? Show of hands. How many of you love setting those things up? Yeah? How many of you enjoy monitoring them or updating them? So for us, it was basically the same issues you had. One of the big ones was scaling. If you get vendor locked into an enterprise solution, they don't like to scale horizontally easily. The other thing is, like I said, it's a pain to configure. Changes to your web API might ruin your day. So if you're, like we deploy really quickly and rapidly in our environment, same as Etsy does, someone might change something and a rule might match something that would cause traffic to go away. So it requires continuous effort. And it kind of feels like you have to jump through hoops the whole time. So while digging around and looking at mod security, we run Nginx, not Apache. Mod security at that stage did not have support or good support for Nginx. I ran across something called Naxi, which is an open source project. It's written in Lua. It is a web application firewall for Nginx, but they still have big rule sets. So we came up with the idea of why have something complex when something simple would actually just work. And basically what we do is we have a couple of regexes, trigger words, keywords, and we base that off a couple of assumptions. So SQL injections, if you know how these tools work, require a lot of requests to actually exfiltrate the data. The same with XSSs. Usually they tend to be tested. Black box scanners usually throw stuff against the wall and see what sticks. So you get a lot of spikes and you get a lot of types of requests that would contain keywords. And this is actual output from people scanning affiliate sites, so partner sites that actually plug into our backend. And you can see at the top there, that's a SQL injection being tried through a file upload field on the name of the file. And I've just condensed down the output, so that's an attack score. We found 12 things in it, and as you can see, this is really easy to filter on. We like detecting stuff before blocking them automatically because emergent behavior. So this gives us the opportunity to take action outside of the request context. So we can fire off an alert and block on the front end through other APIs instead of letting, mod security do this on a web layer.
Or we can just watch them and see what they do and then develop behavioral analytics on top of that so that we're not limited to simple keyword searches. So how many of you guys are storing log data in ElasticSearch right now? Yeah. How many love ElasticSearch? How many have had zero problems scaling ElasticSearch? Yeah, okay. So we've broken ElasticSearch pretty good. We were actually working very closely with Shai at the very beginning when the logging use case was still his secondary vision for ElasticSearch. I remember having several conversations with him where he's like, but it's for front-end search, it's for disambiguation, these things are awesome. And I was like, well, it works really well. I've been able to scale it. So there's a few lessons that we learned, and we actually learned these through testing, not through just following someone's random advice on a blog. One of the biggest pieces of random advice you get on blogs is don't go over a 30 gig heap in Elasticsearch. I can verify with testing that there is no performance gain from going to a 60 gig heap in Elasticsearch. You're better off with two 30 gig instances on one node than you are with one massive 60 gig instance. It actually performs twice as good with two 30 gig nodes or instances. You should leave about a quarter of the memory available for the file system cache that's been talked about a few times. It just gives enough space for all of those documents that are on your disk to come up and be visible. Our deployment was started before Elasticsearch could tribe. Has anyone used the tribing functionality of Elasticsearch where you can have multiple clusters and join them together with a kind of what they call a tribe node that is in both clusters but not really? Anyone tried that yet? Yeah, so we needed we needed a cluster in each data center, and we needed to make sure the shards weren't jumping between the data centers. We accepted the fact that if we lost a link between a data center, we would lose visibility of the logging information in that data center, but then we wouldn't have to incur any cost of replicating that data across data centers. So we have a ton of shards because each day has double or triple the amount of shards that it would normally have because we're sharding across data centers. So there's the default in like Elasticsearch 1.2 switched from what is called the NIOFS backend to a memory map system. And we found that when you have, at the time we had something like 15,000 shards in our cluster, and when you have 15,000 shards and they're all memory mapped, that can use like 10% of that 30 gigs of memory just to keep track of where those shards are. So if you use the NIOFS backend, you cut out that overhead and it just takes a little bit longer to find shards, which is fine. If you're using Elasticsearch and you haven't read the Call Me Maybe articles on the CAP capabilities of Elasticsearch, you really should. 100% of the data we send into Elasticsearch is not available, and 100% of our search results are not 100% accurate. We're okay with that. If you're not okay with that and you're using it, you might want to read these articles to understand those failure cases. We also found out that disk speed wasn't that important. We did drop some SSDs into the cluster, and we didn't gain too much from them, simply because Elasticsearch does most of its work in memory. We also found that we needed to split master and data nodes separately. There is no data on our master nodes, and our data nodes cannot become masters, which is very important for consensus in Elasticsearch, so that you don't end up with corrupted data. There's a few settings that come from a blog post that the guys at Elasticsearch wrote up after dealing with a lot of our failures. One of them is the refresh interval. Basically, setting this interval to a time period means that for that time period, none of the data that you've sent in is available for search. It's like a memory buffer that is not ready to be searched. So for us, we've chosen a 30-second window, which means any log entry we send into the system is not readable for 30 seconds. You may need to tweak that if that's not comfortable for you, but we're okay with that. We also dropped the merge scheduler to only allow one merge to occur on any node at any given time. We found that we had multiple merges occurring at the same time, and when one node had two merges occurring in both its instances, it would out of memory itself, which then caused the cluster to go out of memory because those merge operations would move to another node. So we limit that down to one, and we're okay with it. The transaction log is the actual pre-Lucene segment that Elasticsearch designs to give you the real-time search capability. The default, I think, is just like 32 megs or something of transaction log size. We set that out to 1 gig. This results in fewer Lucene segments on disk, which is less maintenance to handle. And then there's lots of data that's cached. This is why Elasticsearch is so fast. Everything is cached in memory. So you might need to tweak your cache settings to set reasonable ceilings on the Elasticsearch caching. Here we just cache the field data cache, which is how you perform aggregations and things. So our index layout kind of looks like this, where we have our data center IDs as part of our index names. This is the name of where we dump all of our access logs. So we actually have several indexes that match this format, which is nice for being able to assign a template and say, these shards can only allocate in this data center, and these shards can only allocate in this data center. So that gives us that pre-tribing functionality of having one cluster, but the data only exists in one place. But Kibana and things like that expect the names to be consistent, so we have a process for automatically managing all aliases. So we roll up all of these aliases. So if both data centers are available and you search in the access index, you will actually receive results from both data centers. Some things that people find shocking at first. Elasticsearch is a schemaless data store, but you need to use mappings, which are basically schemas for your schemaless data. There is no panacea of fast schemaless searching. You need to tell Elasticsearch what you expect. Don't use the feature auto-expand replicas. I believe it's been disabled by default now, but it will result in massive data corruption. And the fewer replicas of your data that you have, the faster write speeds you have. So even by putting disks into RAID 0, we weren't able to increase performance, but when we dropped the number of replicas in our cluster for today's indexes down to 1, so we could lose 1 node and that was it in our cluster, we saw dramatic performance increases and saw nothing out of going to RAID 0. Something that I stumbled across I didn't know, 8 bytes of memory are used for every document you have in your index on every instance. So if you have 2 billion documents in a single instance, you might be using 16 gigs of RAM just for the storage of the pointers for the documents to where they live on disk. And you can't get around this. So you need to monitor the number of documents you have on each node. Analyzing fields is really expensive. If you can afford to not analyze fields, don't. Instead, chunk the data like we demonstrated earlier, where you have the key pieces you want to pivot on and search on chunked out into individual fields. It actually saves disk space to do it that way than to analyze the field through some fancy analyzation. And agree on a standard for field names. Like this, you could basically, what you're going to end up doing is inventing your own. Try searching for log standards, log field standards, and you'll get about, I think, 45 different standards I was able to come up with just in a little bit of research. You're going to need to monitor and maintain your cluster. We started doing this very early on. I have a suite of utilities for managing it written in Perl that handle everything. They're well documented, pull request welcome. So now the fun part. We have the data in the cluster. Now we need to do something with it. So we wanted to kind of give you an overview of what we started out doing and what we found as we were doing it. So this is Kibana. I'm sure everyone in this room has seen screenshots of Kibana before. And it's just a very basic overview of access activity on our site. The blue line down here is our main website, and it accounts for the majority of our traffic, which is why it's separated from the rest of the roles on the top. And then we just have an overview of how busy each one of our sites are over here, the busyness by country here, and then we talked a little bit about the attack scores here, and you can see that there was a spike in bad URLs coming in at this point over here. So then you can dig down into these things and get more information about them. This is the looking at individual parts of the web attack score and breaking it down. So you have at the top all of the instances of attacks. So that's the frequency that a request is coming in that is scoring against our attack scoring algorithm. And then at the bottom is a summation of all of the scores that we've managed to assemble. So the scoring system works by saying, okay, we found these bad tokens, and then we also look at the server response code. So if the server responded with a 500 error and we saw like bad stuff in the URL, that's more severe than if it returned to 200 in most cases. So those 500s are promoted in the attack scoring system. And then you have a breakdown of what is being attacked. Here, the source IPs of the attackers, which we didn't blur intentionally, and then the countries. And you can see that my home country is the most frivolous with web attack scanning.
And the funny thing is, they keep on scanning out static servers for some reason.
Yeah, see, our static content is the most frequently attacked. This was a lot of fun because we're not just doing this with access logs, we're doing this with all of our system logs. And our goal is that our system administrators and our developers should never need to log into a system at all. So what we've decided to do is we deparse all of the SUDOERS logs, and then we throw that into Elasticsearch, and now we have a SUDOERS wall of shame. And this is interesting for a few things, because you can see along here that there's someone running a sudo command in a while true loop at the top. The top is username. So this person is running some sort of escalated command in a while true loop, right. Probably in tmux, because it's running constantly.
The command that that person was running is ls-of, and it's ran 23,000 times in a little short time span. And most people don't realize that this has an impact on server performance as well. There's another dashboard that we don't have a screenshot of, which is not the sudo logs. We use OSEC in our environment to monitor stuff. So we pull in the LDAP logs as well and correlate with OSEC events. And then you start noticing interesting cron jobs that people have set up, for instance, that log into the Git tree, pull stuff, or do SCPs or rsyncs. And yeah, also a lot of network throughput that you can save basically because you don't have to sync the whole Git tree, which is quite big, every 5 minutes, for instance, to your local laptop. That's why we have a dev environment. Anything else you want to say?
Well, this type of overview is very easy for me to show to the CTO and say, we have developers who are doing things that are dangerous. Look at this. You know, we can point to a line on a graph and he can understand it, which is really exciting. The other thing is we weren't the only ones using the system. We introduced the system to the company. We were primarily using it for incident response and analysis and forensic investigations, but we knew that it had value outside of what we were doing, but we didn't know where that value would come from. So we have a very large graphite infrastructure, probably one of the largest in the world. It's massive. There's all kinds of optimizations that we've done, and one of the optimizations that we've done is we actually split the human rendering from the machine rendering, and we're using a separate API service for rendering metrics for cron jobs and such that are doing monitoring off of graphite metrics. But when we did that split, not all of the services were converted to the API service. So this was a dashboard that one of the guys who was scaling the graphite infrastructure came up with in order to hunt down all of the servers that were still pointing to the graphite the graphite human rendering API when they should have been using the machine readable API. And this was really cool to see. I didn't even know that this thing existed until I started digging into our Kibana logs when I was preparing this presentation. Another thing was we got slow page monitoring for free. I mean, we already had it in our business intelligence platform, but this information in our business intelligence platform is designed by developers for developers. So even for some system administrators to get their heads around the business intelligence platform is very difficult, and you have to know Perl, and you have to know all of these cryptic commands that are passed as tribal knowledge, or if it doesn't show up on a graph, right? With this, people were able to dig into this information and start to look at, you know, mean response times by country and by individual page. At the top, you have mean response time of the slowest pages for each role. So you can kind of see when spikes occur and correlate those things with events in our system. And sometimes you even find that the country is actually significant, that rendering a page for a French-speaking audience may take longer than rendering a page for an English-speaking audience because of a misfire in an experiment somewhere. So these things can help you root out problems that you haven't even thought about. And that's a lot of fun, and it's very visual, and it does a lot to bridge the gap between us security people and developers, sysadmins, and business folks that like to see graphs. Like if you're after graphs, Kibana is a great way to get that information. But we weren't really looking for graphs. We were doing incident investigations and analysis, and those things take time to do, and you need to be able to dig and tweak things. So we built a tool very early on to query Elasticsearch and give us results back on the command line. This is just a very simple search across one day of data that gives us the first three results that have hit a 404 on our main page, shows us the source IP country, and the file here. You can see that the query string is actually, we do pre-parsing of the query string before we send it to Lucene to optimize it for the end user to use. So our lowercase and, which is not a reserved keyword in Lucene, becomes an uppercase and in the query string, so you don't have to remember to do these things. Then you can find top source IPs really easy. Top talkers is simple. You tell it to show me the top source IP. We hit the top three. Go ahead and hit. Those are all Google bots crawling our site. And again, you see the query that was output as well.
So remember that this is an aggregation, and the amount of metrics that Brad said, syslog messages that we actually process, a lot of that's access log data. Look at the response time. So that query to work out for a day, yeah, that was for a day, took 5 seconds.
So Elasticsearch also provides a lot of these really cool features like nested aggregations and different aggregation functions. So we extended the utility to be able to do additional things to help us in our security investigations, because sometimes we're interested in the weird stuff, not just the most frequent stuff. So one of the features that you have with Lucene is cardinality in a field. And we added a -by flag to the utility so that we could look at the top 3 pages by the distinct originating source IP country. And we ran that query, and this was against a cold cache for this particular field because we weren't checking source IP country before. And we end up with the top 3 URLs that are most frequently hit by the most unique source IP countries. So here you see 239 source IP countries for /. Sometimes we were writing these ridiculous awk scripts to take this data out of Elasticsearch and cram it back into queries. So Willem would call me over and he would show me the command that he just ran, and it would take up his whole terminal window.
The awk script would be about 3 or 4 lines.
So we decided this should be a part of the tool. So you can take information like this and say, send this data out to the topattackers.dat file. And then you would get the output as normal, but the next time you ran the script, what you could do is you could actually take source IP : topattackers.dat and then do an array offset of the last column in the field, and that will actually be auto-expanded in the search. So that you can use the output of one query to form the input for your next query, which aids immensely in investigations. So you end up getting these results back, and you can see here that the query was transformed into a terms and query string query automatically.
And all of this actually stemmed from, so this utility evolved because people started, well, bad guys started noticing us, and we started getting phished. We fixed a lot of stuff since then, but you know, for phishing tracking, the utilities that we just showed, especially Kibana, actually enabled us in a really short amount of time. I think it took about a month before we got it completely under the knee, but it gave us the ability to track phishing attacks in real time, which means we could lock accounts that were giving their details away in real time. It's kind of sad if you sit and look at a dashboard and you see things ticking by. But the point is that we had a way of immediately getting the impact, seeing which customers were affected, which hotels were affected, and immediately act on it, which has put us, our turnaround time for phishing sites from when they go live is usually within a 24-hour period. We know exactly what has happened, where the site came from. Even for the tricky ones that actually use proxy servers where you don't actually see stuff, we usually, and we're really good at looking at data, so we have a couple of pivot points, which I'm not going to share, that we use to track stuff. Sometimes we even know when a phishing site's been spun up before they've actually started the mail campaign. And this is an example of the type of data that we looked, that I spent lots of time looking at. This is actually condensed down, so this is actually the bad IP. Some of the common denominators you can look for is speed of access, user agent. I mean, how many people know of a user agent switching between Firefox and Windows? I can't see the thing.
Yeah.
Hold on a
little
second.
bit off screen.
And as you can see that there's a Go user agent in there as well. So it turns out that these guys wrote a script using Go, and it had a bug in it, and the Go user agent rotated through there as well. We've seen these attacks increase in complexity. So initially when we got phished, it was, did it match the geolocation? Elasticsearch makes that really easy to track back. Give me the top source IPs for 3 months that have logged into this hotel. Where are they from? Oh, this one's the odd one out. What did this IP do? Et cetera, and so forth, and Bob's your uncle. Then they started using proxy servers inside the same country. Different ISPs, we log that data, so again, easy to track. Then they started using the same ISPs. So if you look at countries like Africa or South Africa, IPs rotate on a 24-hour basis. So a malicious IP might be a good IP in a couple of hours, depending if they reset their router. So you have to be really careful and look at the statistics and what they actually access. We do behavioral analysis in a sense where a hotel usually uses extranet and will view 5 bookings a day. Why would they then view 20 bookings a day? So there's all of these things that they've started catching up, and you can definitely see that the phishing stuff is a business. They've even added random sleeps. We still catch them. So the data that we get from actually using Elasticsearch and just plain old access log data is really, really useful.
And it turned out to be the simple stuff was the most reliable. This particular bug, or maybe it's not a bug in the Go package that just wants to attribute the fact that it is actually the Go package. This use pattern was able to allow us to identify attacker IPs within a minute of those IPs being used in an attack. So just by seeing these types of use patterns, we were able to action and protect our customers and hotels. I think.
You can also use this for threat intelligence. So like Brad said, when you log, it's not typically that good to do intelligent things while the data gets stored, but you can run the data from the ElasticSearch tool through other things. Okay, so Bro Network Security Monitor, anybody knows Bro? That actually has a ElasticSearch backend option where it can store TCP dump data and stuff like that, PCAPs, notifications. It's actually a network intrusion detection system, but you can use that as out-of-band intel to see if this IP has actually hit anything else on your network. Collective Intelligence Framework is a tool that actually parses things like ShadowServe, Zeus Tracker, all of these threat intel free feeds, and it also sticks it in Elasticsearch. We actually use it in our internal tools to flag IPs with extra bits of data. So if a dev sees, man, there's a big error spike, and he hovers his mouse over the IP, immediately that information's there. You know, this is part of a botnet. Do you want to block it? Yes, and it's blocked. So we kind of crowdsource that type of stuff. There's ElasticAlert and Watcher. ElasticAlert was released by Yelp. It's a Python framework that basically allows you to do alerting. It's easily extendable, but you need to know Python to actually extend it. Watcher was released by Elastic Co. last month, I think, or 2 months ago. It's still in beta, but it can also alert on anomalies and statistical anomalies in your data. And it might seem like magic. Any questions?
Really no questions? Yeah, there are. Are you just picking up your phone, aren't you? Did you benchmark the doc values support in Elasticsearch?
The what?
Doc values.
Doc values?
Yeah.
No, we haven't really played with that too much. Some of our front-end searching was using that, and it kept failing in production. So we tried to keep to the simplest use cases possible and see what we could get just simply out of those things. So we're not really using like scoring of documents at all. We're not using anything like Percolator or any of those more advanced features, just because we're able to get so much out of this, and we've managed to get the cluster to scale to a reasonable level with these things. Actually, our problem is mass adoption now. We started out with 2 indexes and 1 user, us, and now we have basically 7 main bases, which include the networking equipment, some monitoring that comes from our proxy logs, Agari reporting on DMARC protections. Like, we have a ton of these use cases coming in now that we're actually having to tribe our nodes and split our clusters because they're just getting too big.
Answer your question? Yeah, Kinda. Fine during coffee break.
Yeah.
Any other questions? You told so much, and no questions left anymore. They probably will attack you during your coffee. Thank you very much, Willem.